honored to be able to talk about my research at this conference, ESCMID ASM 2024. Thank you for the opportunity. My name is Ji-Hoon Kim, and I'm currently a PhD student in Dr. Won-Sing Lee Laboratories at Seongkyungan University from South Korea. I'd like to share our recent finding on how targeting the bacteria signaling molecule, cyclic AMP, can help us overcome beta-lactam antibiotic resistance, particularly in methicillin-resistant Staphyloccoccus aureus. Beta-lactam antibiotics are still widely used around the world for treating bacterial infections. Beta-lactam antibiotics block the transpeptidation of peptidoglycan in bacterial cell synthesis. The toxicity profile of these antibiotics is well established, and it is cost-effective to produce due to the established synthesis process of beta-lactams. However, infections caused by beta-lactam-resistant bacteria are increasingly common and major cause of severe disease. Typically, beta-lactam resistance occurs when beta-lactamases are produced to break down beta-lactams. Beta-lactamase inhibitors like clavulanic acid have been created and effectively used in clinics to combat resistance caused by beta-lactamase. However, MRSA also carries a resistance gene cassette containing BAG, which encodes the beta-lactam resistance penicillin binding protein PP2A. PP2A exhibits weak binding to most beta-lactams, allowing it to maintain PG cross-linking even in the presence of beta-lactams. Newer generation of beta-lactams, including ceftaroline and ceftobiprole, have been created to combat MRSA's resistance to beta-lactam caused by PP2A. However, resistance against these antibiotics has already emerged in the clinic. Therefore, finding strategy to overcome beta-lactam resistance by PP2A is of great importance. I searched through many papers to find new target and concluded that modulating the metabolic pathway of bacteria would be a highly effective strategy. Cyclic AMP regulates various physiological processes in bacteria, including osmoregulation and maintenance of the integrity of the bacterial cell wall. In S. aureus, it is synthesized by the enzyme DAG and degraded by the enzyme GDPP. In addition, mutations in the GDPP gene have been found in beta-lactam resistance clinical strains. So, I found a compound that could reverse the resistance of beta-lactam antibiotics, the celastrol, and treatment with celastrol significantly reduced the level of cyclic AMP in bacteria through activation of GDPP. This regulation of bacterial metabolism reduced the cross-linking rate of the cell wall and indirectly inhibit the cell wall synthesis by PP2A. We examined the celastrol as a beta-lactam potentiator in a mouse sepsis model. The animal model co-treated with methicillin and celastrol survived, while methicillin or celastrol alone did not effectively protect the infected mouse. So in conclusion, this study demonstrates cellular cyclic AMP as a potential therapeutic target in a combination treatment to reduce beta-lactam resistance. The development of antibiotic potentiators that target bacterial metabolism is believed to be an effective strategy to address PP2A-mediated resistance and to overcome a limitation of beta-lactamase inhibitors. We envision that our finding could be applicable in discovering of antibiotic potentiator scaffold and identifying an lesser metabolic pathway whose modulation can be explored to reduce antibiotic resistance. Thank you for your attention.